Okay, so we will begin right away. Okay. Okay, is my screen visible?
Yes, sir.
So,
Yes, sir.
Okay,
Yes.
okay, then let us proceed. So we will begin by reviewing the biases theorem. As we have said, biases rule, it deals with the events of the real world. I mean, what this theorem actually does is it quantifies, it mathematically formulates the operation of beliefs that continuously get updated in our brains. And so in a way, it is something that is inherently familiar to us, although maybe without our active awareness. And that is a way to think about many of these problems related to joint probabilities and conditional probabilities. And specifically in case of bias theorem, one way that helps sometimes formulate these problems is to think of the situation as underlying causes that influence the outcomes, right? Now, what is quite interesting is that this model that we have developed, this type of visual representation or the graphical representation that we have developed for some problem of the real world, when somebody has certain symptoms or that person goes to the laboratory and does the test, whether the test comes out positive or negative, t is equal to 0 or 1. Based on that, we have to infer whether the disease is present or not. That actually is very much like what happens when a communication transmitter sends C equal to 0 or C equal to 1, when it sends one bit at a time. And that bit goes over the noisy channel. And the effect of the noisy channel is to sometimes flip the bit. So C equal to 0 sometimes gets flipped and gets received as T equal to 1, or vice versa. Now, although the mathematical model of the communication channel, a very simple model, you would not find it too difficult to accept that such a model can arise. You know, if you have the hard disk on your computer, or if you have this USB drive in the sometimes you may even be using DVDs and CD-ROMs and all those types of memory devices. Suppose there is something wrong with some part of that memory, right? One very good example is the CD disk, and that has maybe some dust particles deposited on certain portion of that CD surface. And now when you insert that CD into your, because of those impurities, what is printed on the CD might be read by the computer in exactly the opposite manner. Actually, the CD and the memory drives, other memory drives, contain a sequence of zeros and ones. And most of the time, those zeros and ones are read correctly, but maybe sometimes 0 gets read as 1 and 1 gets read as 0. And that is correctly captured by this type of communication channel. And then the task at the receiver of a communication system is to see when the CD head reads a 0, from that, let's say t equal to 0, or in some cases we have called it y equal to 0. From that, it has to decide whether x was actually 0 or x was actually 1. Now, if these red colored lines were not there, if they were not present, then the situation would be very simple. Only the green colored arrows are there, and so whenever you read x equal to 0, you go back and say that the transmitted symbol must have been 0. But otherwise, there is a fundamental ambiguity. X equal to 0, or sorry, y equal to 0 or t equal to 0 in this case could have come either from c equal to 0, or there is a small chance that it could have come from c equal to 1 as well. Okay, so that is the essence of the communication reception problem. And in context of Bayesian rule, we then have to start thinking in terms of conditional probabilities. Probability of observing a particular outcome given a particular cause is in effect. Probability of y given x. And that we have called the likelihood function. Similarly, we will also make use of something called the prior. What are the chances that a general, a randomly selected person in the entire population is infected with this disease? Maybe that prior is known to us, or maybe we make an estimate of it. So the probability of the causes, which is called the prior probability of the causes, is sometimes also available to us. And then using this to P of xi and P of y given x, we can then use that marginalization of the joint probabilities. Remember that very important formula that we did last time. So using that, we can calculate the probability of y also. So this is not known to us ahead of time, but it is direct calculation given likelihood and the prior. What Bayes rule says is that once we know all these three values, likelihood, prior, and the evidence, then we can calculate the posterior probability on x of I. And that calculation can be applied to many real world cases, as we have seen last time. And the specific formula allows us to then go back on this graph. When we receive a particular measurement, t equal to 0, then our interest is to determine whether c is equal to 0 is more likely compared to c equal to 1 or not. Okay. If we get tested for coronavirus and our test result comes out negative, we start celebrating, say, oh yes, we don't have coronavirus. And that is because we are, without maybe our active awareness, we are calculating the relative possibilities that we have the disease versus not have the disease. And our brain concludes that the probability that we don't have disease is much, much greater than the probability that we have the disease because our test came out negative. A lot of the times we just assume that probability of c equal to 1, the posterior, not the prior. The posterior after we take the test is pretty much 0, which is, by the way, not the case. Okay, according to this mathematics, there is a small chance that even if the test comes out negative, maybe that test result itself is wrong and the person has the disease. So the correct thing to do is to look at the probabilities of c equal to 0 and c equal to 1 after getting the test. And that is called the posterior. And similarly, suppose if somebody gets tested, its result comes out positive, then again the person has to evaluate the relative possibilities of c equal to 0 versus c equal to 1. And how to do that is formulated by this theorem from Bayes. You will see that the numerator is the product of likelihood and the prior. Remember, prior means the prior probabilities that we assign to the causes. And the likelihood is the probability of observing a particular outcome given a particular cause. And so if I multiply the two, in the numerator, what I get is just the joint probability, y and x, the intersection of y and x. Because this is how we have defined the joint probability. It is the product of the conditional times marginal. And so now if the numerator is p y of j x of I, and if I divide it by p of yj, then again by the definition of conditional probability, I get the posterior probability of x given y. Right? So this very simply is what the Bayes rule is all about. It's a way to transfer the conditional probabilities of y given x that we have, the likelihood function that we typically know. This is a way to transfer the likelihood function to the posterior. Okay, so this is probably one of the most important rules, I would say, of the probability theory as well as the estimation theory. And this is something that we will be practicing a lot. Actually, I have given you already one assignment, lab number 3, that I think is due tomorrow. And all that it does is asks you to practice with this equation over here. So let us then formalize our discussion and cast it in the language of communication systems. So we are going to consider the exact same diagram that we have before, except we are going to introduce symmetry. So what do I mean by symmetry? You will see that in this general diagram, I allowed these marginals to be defined by two different values, p error 0 and p error 1. Right? So these are two different values. I can allow that the errors that happen when c is equal to 0 may be different from the errors that happen when c is equal to 1. The summation of the likelihood for c equal to 0 is always 1. So 1 minus p error 0 plus p error 0 has to be 1. And similarly, the summation of likelihood for c equal to 1 also has to be 1. But the individual values may be different. I can make this equal to 0.7 and 0.3, whereas here I can make this equal to 0.1 and 0.9. So this is the general case. Now for the communication system analysis, we will take a simplified version of this general case where there is a symmetry. So p error 0 and p error 1, I am replacing it by same value, p, small p. And this is justified intuitively. You know, this example of CD-ROM that I gave you, the dust particles don't know that they are sitting either on top of a 0 or top of a 1, which is printed on the CD, right? They just randomly go and distribute themselves on the surface of the CD. What I'm trying to say is that in the communication context, the channel flips 0 into 1 and 1 into 0 without any bias. It doesn't care whether the underlying bit is 0 or 1. It just flips it. And therefore, we have no reason to believe that the zeros will get flipped into 1 any differently from the ones getting flipped into 0. So the error probability or the crossover probability, I would say, 0 into 1 or 1 into 0 is symmetric. For 0, the value is p. For 1 also, the value is p. And that is why this is called a symmetric channel. So it's actually a simplified case of that Bayesian channel that we had looked at earlier. Now let us look at this in a little more careful manner. Okay, so remember, what we are trying to do is, at the communication receiver, we have observed y equal to 0. And now we want to decide whether the transmitted bit was 0 or 1. And or we may have observed y equal to 1, and again our question is the same, whether x is equal to 0 or x is equal to 1. So in such cases, we probably don't care about the exact probabilities, exact values of posterior. All that we want to know is whether after observing y equal to 1, whether x is equal to 1 was more likely than x is equal to 0. And this sometimes is true even in the real life, right? So if you get tested for a disease And then the next question is whether you have to be hospitalized or not. Then the decision has to be binary. You either get hospitalized or you don't get hospitalized. So yes, exact probabilities are important. It's good to know how confident you are, whether you don't have disease or you have the disease. So that level of confidence is measured by the exact values of posterior probabilities. But then a lot of the times we want to also decide in a binary manner, yes or no, whether the transmitted bit is 1 or 0. And in that case, a very clear strategy is to just look at the posterior for x equal to 1 versus x equal to 0, given that y is equal to 1. And if the posterior on 1 is greater than posterior on 0, then we say that the transmitted bit was 1. Otherwise, we say transmitted bit was 0. Right? Now, I hope that this is clear to you, because you see this actually allows you to understand very, very important mathematics, or actually even an important scheme, or even an important algorithm of machine learning. This is called maximum a posteriori decision rule. If you pick up any machine learning book, if you pick up any estimation and detection theory book, or if you just do an online search on this map decision rule, you will get a lot of content, a lot of tutorial level explanation of the map rule. It is one of the most fundamental rules of the learning algorithms or the learning techniques. And this is all there is to it. Okay? Is essentially in the map rule, we have made some observation and we are trying to determine whether this is more likely or this is more likely. And the way we do that is by using the bias technique. So before we get into the mathematics, I want you to be absolutely comfortable with this map technique, right? The name may seem fancy to you. Maximum a posteriori. This word posteriori is like a little bit strange word to most of us. We typically have not seen it ahead in our life. I don't know where it came from. Maybe it is Latin word converted to English, or I don't know what it is. But all that it is you are trying to decide which cause was more likely after you observe a particular effect. So that post word comes from the after part of it. You have observed something, and after that you are trying to determine what the relative likelihoods or relative probabilities are. So this posterior part is to be contrasted with the prior probabilities. See, the prior probability of x equal to 1 or probability of x equal to 0 is before you take the test. Generally, what are the chances that if you pick any random person, that person may or may not have taken the test? What are the chances that that person is infected? That is called prior. You don't even enter the picture at that point. Posterior is when you have taken the test, you have observed the outcome of the test, and now you want to determine for yourself what are the relative probabilities. And that is where the posterior comes. And the word maximum is because you are doing this maximization. Which one is more than the other? Probability of posterior x equal to 1 is greater than probability of x equal to 0 posterior, then I will be worried. I will say that I have the disease, right? So that is where this different terms in this name come about, maximum and posterior.
Sir,
But
well,
the underlying idea you should be very comfortable about. you go back to that graph that we have drawn, and all that you are doing is going back on that graph and just weighing which one is the more likely possibility. Okay, so once you are comfortable with the basic concept, then the math is just direct. It follows directly from the Bayesian rule. And so what we are going to do, at least for the binary case, is we will evaluate this ratio. And that ratio we are going to call lambda 1. Why lambda 1? Because we are evaluating the ratio of the posterior when we have received y equal to 1. So this one here in lambda 1 is because we are saying y is equal to 1. And we are taking the ratio of the posterior x equal to 1 versus x equal to 0. So this is lambda 1. Remember this. This is pretty important formulation. What we are doing is going back in this situation. We have received y equal to 1, and we are taking ratio of the posterior on x equal to 1, x equal to 1 versus x equal to 0. So that is what lambda 1 is. Now, if you plug in the Bayes formula, this ratio turns into this. And all you need to do now is plug in the values. So y equal to 1 given x equal to 1, that likelihood we have called 1 minus p. The prior on x equal to 1 we have called q, because x is a Bernoulli variable with parameter q. And similarly, you can look at the denominator. It turns out to be p times 1 minus q. So this lambda 1 is just one number. It's a single number. And even non-mathematicians, even people who are not familiar with probability theory or estimation theory, they actually use something like this. And they call this odds in favor of x is equal to 1. Right? X is equal to 1 is the case that we are comparing against x equal to 0. And this ratio tells us what is the likelihood of x is equal to 1 versus x is equal to 0. And that loosely in the English wording, it is called odds in favor of x is equal to 1. And so if this ratio lambda 1 is greater than 1, it means that this prior on x equal to 1, posterior on x is equal to 1 is greater than the posterior on x is equal to 0. And so you will say that I will decide that the transmitted bit was 1. My decision regarding transmitted bit I am denoting by x hat. So the rule is, the map rule is that you calculate the ratio lambda 1 when you get y equal to 1. And then if that ratio is greater than 1, then you say x hat is equal to 1. If the ratio is less than 1, you say x hat equal to 0. What if the ratio is exactly 1? Any thought?
Both are likely.
Equally likely.
Both are
Equally likely to
same
occur.
chance.
Equally likely to occur.
Exactly. Both are equally likely, so it doesn't matter. You can either say x hat is 1 or you can say x hat is equal to 0. You can pick either one. Now, one other very useful rule that also you will come across later in your studies is called maximum likelihood rule. Sometimes maximum likelihood is even more popular than map rule. The only difference between ML and map is that ML assumes that Q is equal to 0.5. q, the prior is assumed to be 0.5. And so obviously when q is equal to 0.5, q and 1 minus q are the same. Both the values of the prior are identical, and so that part cancels out and the map becomes just 1 minus p divided by p. But 1 minus p divided by p is just the ratio of posteriors. Sorry, is the ratio of likelihood. 1 minus p is the likelihood function of receiving 1 when transmitted bit was 1. P is the likelihood of receiving 0 when transmitted bit was 1. And so the ratio of posteriors becomes just the likelihood ratio. So when would the ML rule be more appropriate compared to the map? And when we have to use map?
When priors are equally likely.
Right. So when priors are equally likely, you might as well use ML. I mean, you can still use map, but then for map, you have to do one more computation, right? Q divided by Q, 1 minus Q. But when the priors are known to be equal, then why to do that? We'll just use the simpler version, which is ML. But when is that justified? When are you justified to use ML instead of map? Well, a lot of the times at the communication transmitter, zeros and ones are occurring equally likely. Communication transmitter doesn't favor 0 versus 1 a lot of the times. Sometimes that is not the case, but more or less, that is the case. So one example is you take a photo from your digital camera, and let's assume that the photo is sufficiently complex scene, right? It's scene of some natural landscape, or maybe scene of somebody's face, or maybe your drawing room or kitchen or something like that. Then there will be equal amounts of shades of different colors. There will be equal number of zeros and equal number of ones. And so we can kind of roughly assume that Q is equal to 0.5. So if you're transmitting such an image, let's say on your WhatsApp, then that phone which actually transmits your image, for that, the phone can be thought of as a Bernoulli transmitter with Q equal to 0.5, because zeros and ones mostly are occurring with equal probability. But maybe there are certain cases where that is not the case. So certain scenarios. So one example is, let us say if this WebEx link is going on, and hopefully you're looking at my video, and you will see that the background is of the same color. And so most of the part of this video capture, that is what you are seeing, is mostly represented by just the same bit. If this red color is represented, let's say, by 1, then there is a lot of ones for maybe 3/4 of this video frame that you're looking at. And so in that case, it will not be justified for us to say that Q is equal to 1. Sorry, Q is equal to 0.5. Right? So that those are some of the real world cases. I mean, obviously, if you are considering not the communication system problem, but some real world problem, like this coronavirus problem, then definitely Q is not 0.5, right? I mean, right now we know that the situation in terms of this pandemic has worsened, but still it is not Q is equal to 0.5, thankfully, thank God. If it was Q equal to 0.5, forget about it. I mean, all hell would break loose at that point. Right now, Q is probably still less than 1%, I would think. So in such cases also, you can't use ML. You have to go back to math. But a lot of the times ML is justified and then it simplifies the Bayesian mathematics. You will say that, well, there is not a whole lot of simplification, right? Compared to this expression of lambda 1. Over here, lambda 1 got simplified, but not a whole lot. Yeah, that is because we are assuming binary case. But as we progress along and we start considering non-binary cases, then this simplification actually does help a lot. Okay. Now, one more thing is that we have to be absolutely clear about what we are doing by map and ML. And I will repeatedly ask you to go back to these two diagrams. If you understand these two diagrams and what we are trying to do by these two diagrams, then the mathematics will not be coming and standing in your way in terms of a deep understanding. So lambda 1 that we were looking at was corresponding to this case. It applies only when you have received y equal to 1. You can't use lambda 1 if you are having this case. Lambda 1 you have to throw out of the window. You have to do a new calculation. When you get y equal to 0. Okay, this is something very fundamental, and in a way it is clear to all of us all the time, but when we again cast it into formal math, then sometimes the situation becomes a little muddy. So I want to emphasize that these two cases are two totally different cases, and we have to do two totally different computations. And the answers that we get will also be very different. Again, going back to the this disease problem, if you get t equal to 1 as the outcome of the test, you are actually worried because now the source, this disease source, and specifically the corresponding PMF, the probability mass function of the source, starts appearing to you kind of heavily biased for C equal to 1 case. And so you're worried that maybe you have the disease. Whereas if you consider this situation that you went and took the test and the result came out negative, you start celebrating because now the PMF suddenly changed completely. Instead of a lot of probability mass getting concentrated in your mind at C equal to 1, now the probability mass in your mind is now concentrated at C equal to 0. Again, let me use even a simpler word, not probability mass. It's this probability mass is actually your belief. So your belief regarding whether you have the disease or do not have the disease, when you get t equal to 0, is vastly different from the belief that you have when you get positive test result, right? I mean, that is obvious. I don't even have to say this. And the reason is because your brain is doing two fundamentally different calculations, t equal to 1 versus t equal to 0. When t is equal to 1, your brain is doing this lambda 1 calculation. And it is worried that maybe this lambda 1 is greater than 1. However, when you get t equal to 0, or in general communication context, when you observe a bit y equal to 0, you have to do a completely different calculation. This calculation is also of the posterior, by the way, but those posterior are for the case when y is equal to 0. And you go through the math and this comes out to be the answer. Look at this formula here. The way that I have defined lambda 0 using this formula Now I ask you that suppose if lambda 0 turns out to be greater than 1, then what would you say?
Decision bit is
Probability
0.
of x equal to 0 is more.
Exactly.
Or
So,
cheating of x
So
equal to
in
0.
this case, when lambda 0 is greater than 1, you are going to say that x equal to 0 is more likely than x is equal to 1. This is different from this case. Here intentionally I put x is equal to 1 in the numerator. Here I put x is equal to 0 in the numerator. Because typically when you get y equal to 0, x is equal to 0 is more likely, right? When your test result is negative, most likely you don't have the disease. So that's why if you compute lambda 0 in this manner, your lambda 0 will turn out to be greater than 1, mostly.
Sir, hello.
Yeah,
So in the denominator, it should be p of x equals to 1 now.
yeah, it is
No,
probability.
equals
Sure.
to. Next step.
Oh, here, yes.
prior.
Thank you. Yeah, this is my typing mistake. Sorry about that. Yes, this should have been x is equal to 1. And therefore, here I didn't make a mistake. Here this is actually fine. Thank you. Thanks for pointing out that mistake. And so again, if the prior probabilities are equal for the binary case q is equal to 0.5, then you get a simpler case of ML. So I want to again emphasize that your calculation when you get y equal to 0 is different from the calculation that you do when y is equal to 1. If you get y equal to 1, then you calculate lambda 1. And whenever lambda 1 is greater than 1, you bias your belief towards the possibility that x is equal to 1. When you get y equal to 0, you calculate lambda 0. And whenever lambda 0 is equal to 1, you bias your belief towards x is equal to 0. One important thing that I want to emphasize, it is kind of obvious, but still so that none of you are confused. You are never comparing lambda 1 with lambda 0. Because you never compute lambda 1 and lambda 0 together. Either you compute lambda 1 when you get y equal to 1, or you compute lambda 0 when you get y equal to 0. And then you compare either of these two, lambda 1 or lambda 0, against 1. Don't compare it against each other. Now, there's another thing that I want to emphasize, that you say, yeah, all this is fine and good, but how do we know P and how do we know Q? Yeah, it's a valid question. That answer to that is a very detailed answer. We are not going to get into that in this course. You can assume that we know these values of P and Q. In reality, you may have to guess it, you may have to make an estimate of it, or you may have to make some measurement ahead of time. For example, if somebody is coming up with a test of a particular disease, they have to do a lot of laboratory experiment to determine what is P for that test. And maybe there'll be some social scientist who will be measuring Q. Maybe they will be conducting kind of an poll of a large population to determine what the value of Q is. And then the other thing I want to convey to you is that this lambda 1 and lambda 0, you think of them as the belief, right? You just now told that when either of these ratios become 1, we say that both the causes are equally likely, meaning that in our brains, we believe that both the situations are equally possible. But what if this ratio lambda 1 or lambda 0, what if it is much greater than 1? What if it is 100?
P can be nearly considered to be very less.
Exactly. No.
Belief will become
We can
definite.
come on to the conclusion that
P is given to you. We are not trying to determine the value of P based on lambda 1 or lambda 0. Remember,
We
P and
can say whatever
they are
taste
the
is,
input
it
to
is
your algorithm. So that answer is wrong. If
we
lambda
can say whatever
say
taste
P is
is,
small,
it is right. Whatever taste says, it is right. Then, well,
right? I think that is a better answer. But again, in terms
Okay.
Belief
of
will be
beliefs,
stronger.
exactly. Your belief
Taste
that
can be considered as almost accurate.
yeah. But I want to say that your belief about whether you have the disease or not, in that, the belief that you have the disease shoots up a lot. Basically, the posterior probability of x is equal to 1 is much greater in your mind. Your belief that the transmitted bit was 1 is very, very large. Similarly, if lambda 0 is very large, then your belief that the transmitted bit was 0 becomes very large. So the values of these ratios much greater or much less than 1 imply a strong belief about the likely goals. Whereas the values which are 1 or close to 1, it means that you can't form a strong belief. In your mind, both the possibilities are about equal. So think of lambda 1 and lambda 0 as kind of beliefs that are getting updated in your mind, the ratios of the posterior beliefs. Okay, so at this point of time, I'm going to take a small break. Just bear with me. My laptop is running out of battery, so I will have to connect it to the charger, okay? So please, there'll be a break of a minute or so. Okay, is the screen visible? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
So let us continue forward. Okay, now other thing is that you will see, maybe I'll show to you some diagrams, and in that you will see that your prior, this Q, kind of acts as a way to, in a way to control your beliefs about the possibility of the two causes, right? So what do I mean by this? Well, again, you know this very well, but when I write it like this, you may be confused about what is the meaning of this. So maybe I'll explain it to you in just a few moments. Okay, so let's continue forward. So this calculation, I hope that you have done yourself. I'm just repeating it for the sake of kind of completion. That for the series problem that I gave you kind of in the very first or second lecture, the calculation, once you formulate it in this manner, becomes very, very, very simple. Okay. So lambda 1 is what you are calculating, because remember the problem says that you have received y equal to 1. So forget about lambda 0. You don't go look at lambda 0, you calculate lambda 1. Lambda 1 is this expression that we have just derived. Now what you will see is that you can actually ignore here both 1 minus p and 1 minus q. Why? Because p and q are so small, 5% and 1%, that 1 minus p divided by 1 minus q is most likely going to be very close to 1. So we ignore that. Then the calculation becomes very simple, Q divided by P, and that turns out to be 0.2. And so then those of you who gave the right answer, all that they did was they converted this 0.2. By the way, 0.2 is the ratio of the posteriors, right? And so let's call them as Q prime. So lambda 1 can be written as Q prime divided by 1 minus Q prime. What happened here? After getting the test outcome of y equal to 1, you updated the prior belief that you had, which was Q, and you made it Q prime. The source still remained Bernoulli. It is still whether you have the disease or not have the disease. Suddenly you can't have 5 different cases of multiple varieties of whether you have the disease or not. That is not possible. Either you have the disease or not have the disease. So the source remains the same. But remember what I told you just a few minutes back, that after you get a particular outcome, the source suddenly starts appearing to you very different. And essentially what is happening is Q is turning into Q prime. And the ratio of Q prime divided by 1 minus Q prime is exactly lambda 1. That is how we have defined lambda 1. But Q prime is now the posterior. It is not the prior. Prior is the general population. Q prime is your own body, whether your body has the disease or not. Or in the communication context, Q prime is about a particular bit that the receiver observes. Q is the general, all the bits that the transmitter sends. What are the chances that out of maybe 1 million bits that the transmitter sends, what are the chances that you will get a 1? Well, that tells, that is formulated by Q. Q prime is different. At the receiver, you have observed 1 bit. And now we want to decide whether the transmitter is more likely to have sent 1 or 0. And that probability of 1 that the transmitter has sent is formulated by Q prime. It is the posterior. Q is the prior. And after receiving y equal to 1, you are updating the prior so that Q becomes Q prime. And that ratio is 0.2, and so you can do simple math and see that Q prime is 0.60. So once you know this technique, the answer to this question becomes very simple. It's just 2 steps. So you will still say that I don't have the disease because lambda 1 is less than 1. But still, it doesn't mean that the belief that you had remained the same. Previously, you thought that there is only 1% chance that I have the belief, because I am like any other person of general population, and in general population, there is only 1% prevalence of the disease. But then if I take the test, my test result comes out positive, my belief about whether I have the disease went up. It became 0.16. But I will still say that I don't have the disease because this lambda 1 is less than 1. Why? Because 1 minus Q prime is 0.84. So I would obviously go with the higher probability situation. On the other hand, suppose if Q was 0.5, the priors were equal. Well, then you can just do the maximum likelihood. And now this ratio lambda 1, instead of remaining a small value of 0.2, it becomes suddenly 19. And so if you do the math, Q prime turns out to be 0.95. So from Q equal to 0.5, you went up to Q prime of 0.95. Now you will say that, yeah, if the person got the test result positive, it's very, very likely that the person has the disease. So what changed? The only thing that changed was Q here was very small, only 1%. Here I made it 50%. And because of that, remember, I didn't make any change to P. P is still 5%. It's only because of this Q that in this case, even after getting y equal to 1, I'm concluding that x is equal to 0. That is this last sentence. The prior is kind of not allowing me to change my opinion too much. Whereas if prior was equal, then I will just go by the accuracy of the test itself. And I will say that the test has 95% accuracy, and so I have 95% chance of having the disease. Right? How to say it maybe even more simply. Let's say that, let's say you have a very good friend, maybe your relative, and you really like that person. As a person, you think that person is very nice. That is your prior. That is your prior belief about the person. Now, suppose one day you observe that person doing something wrong. Maybe that person got angry at you. So after that episode, maybe you two got into fight or something. Well, yeah, maybe exactly when you were fighting, you probably felt pretty bad about the person, but maybe 5 minutes later, you would say that, that person is still good. Maybe there is still a little bit of leftover anger. And so previously you thought that, oh, the person is good. 99%, with 99% belief, I say the person is good. Now your belief became 94%. Sorry, 84%. Why? Because your prior about the person was very strong. You know that person is actually inherently very good, very friendly to you, very nice to you. And so maybe occasionally there is some bad behavior. You don't change your belief about the person. Maybe you change slightly, but not too much. Whereas if you don't know the person at all, maybe hopefully sometime soon you will come to the campus, you will start living with a roommate, that roommate you have never met before. And then the very first episode with that roommate, you will make a judgment about that person right away. So if you have a pre-established belief, in English we call it prejudice. If you have prejudice, then even if you see something opposite to your belief happening, you will still hold on to what you have believed before. I don't want to get too much political, but maybe to even make it crystal clear, you may have seen, maybe you are not too much into politics, but you may have seen maybe your relatives who are either very strong supporter of one particular political party, and they hate the other political party, right? And now let's say this political party is in the power and they make some decisions. And because of the decision, let's say maybe the overall situation in the country, instead of improving, it becomes worse. So if you like this political party, then even if they make certain decisions which actually end up hurting the nation, you will still say that, no, this was good. Why? Because you have a strong prior belief that anything that this political party does is good. And so if you see some evidence which is going against that, you still don't update your belief that much. On the other hand, if you are neutral, then you will just look at the evidence and then decide whether what the party did was good or bad. It's sort of like having open mind versus closed mind. Person who has closed mind, they see a lot of evidence, but they still don't change their belief. Whereas the person who has an open mind, they don't have any prior belief at all. And so anytime they see something, they will update their belief accordingly. So this is the way to think about the belief updates that are going on. Now, I want to show to you certain graphs by which we will see the values that lambda 1 and lambda 0 take as a function of p. Remember, p is that crossover probability of the binary symmetric channel. Okay? And remember, what is the measurement yardstick? We want to compare both lambda 1 and lambda 0 against value of 1. So when on the y-axis, the values are greater than 1, then I'm going to decide that if I observe y equal to 0, I will decide that x was 0. If I observe y equal to 1 and then lambda 1 was greater than 1, I will decide that x is equal to 1. Whereas if this likelihood ratios are smaller than 1, then I will decide in the opposite manner. Right? So let us look at some extreme cases. Let us say that P is very, very large. Let's say P is kind of very close to 1. In this case, what are the values of lambda 1 and lambda 0? They both are almost 0. What does that mean? Remember, we said that when lambda values are either very small, very close to 0, or they are very large, they are close to infinity, then we have very strong beliefs. So at least we can say that in this case, when P is very close to 1, at the receiver, whenever we get a particular bit, either y is equal to 0 or y equal to 1, first of all, we make a very strong belief. And then second of all, what this says is that because lambda values, both 1 and 0, are less than 1, you have to flip what you get. That is how we define lambda values. And that actually makes sense also. Let us take the extreme case that P is equal to 1. And then go back and look at this diagram. So what happens is when P is equal to 1, this green line disappears. It gets erased because 1 minus P is 0. And there is no uncertainty now. Whenever you get y equal to 0, you know for sure that x was 1. And whenever you get y equal to 1, you know for sure that x was 0. And so obviously you have to flip. When you get y equal to 0, you have to flip and estimate that transmitted bit was 1. And same way when you get y equal to 1. That is very clearly captured by this diagram. I mean, this point on this diagram. On the other hand, let's consider this other extreme case, although I haven't plotted this likelihood ratio for values of P less than 0.3, let us imagine that if I did make that plot, this would just keep on climbing up and up and up. It will reach infinity when p is equal to 0. When it reaches infinity, again, remember, it means that you have very strong beliefs about posterior. And that again makes sense because p is equal to 0. So now that red colored line gets erased. 1 minus p becomes 0. And so whenever you get y equal to 0, you know for sure that x was 0. Whenever you get y equal to 1, you know for sure that x was 1. And so therefore, this lambda 1 and lambda 0 became infinity. Your belief about what was the possible value of x compared to the other value, that relative beliefs became infinity. In this case, the relative belief became 0. Basically, this curve here shows the posterior belief ratios for different values of p. And what it tells us very specifically is that in this case, when q is equal to 0.5, when p becomes 0.5, then you have equal beliefs about x is equal to 0 or x is equal to 1, irrespective of whether you get y equal to 1 or y equal to 0. Think about it. This is little subtle, but it's kind of important realization. I'll repeat again that when q is equal to 0.5, in that case, when p is also equal to 0.5, then it doesn't matter whether you get y equal to 1 or y equal to 0, because lambda values remain equal to 1. But lambda values, even before you got any value of y, were anyhow 1. Q divided by 1 minus q is 1 because q is 0.5. Now you got y equal to 1, you calculated lambda, it still turned out to be 1. Let's say you get y equal to 0, and so you calculate lambda 0, but that lambda 0 again turned out to be 1 because p is equal to 0.5. And so in this case, it doesn't matter what you get. You are not able to update your belief. You are not either able to climb up this curve or go down this curve. You are stuck at the value of 1. In other words, the output of the binary symmetric channel is useless. This is important because, remember, we are going through all of this conceptual development so that we can define the concept of information transfer. And on this chart, for this particular point where p is equal to 0.5, what we are concluding is that for such a channel, for such a binary symmetric channel where p is equal to 0.5, when q is equal to 0.5, the information transfer cannot happen. Okay, so that is one observation. Let us look at some other observations. So I want you to look at the value of lambda 1 and lambda 0 when p is equal to 0.4. And so those values are roughly about 1.5, right? If I look at the value of this curve at p equal to 0.4 4, it is about 1.5. So fine. So after you get either y equal to 1 or y equal to 0, you compute the ratio of the posteriors, and it turns out to be 1.5. And so in this case, you will decide that if you get y equal to 1, you will decide that x was 1. If you get y equal to 0, you will decide that x was 0. That is for q equal to 0.5. What happens if q becomes 0.1? Now I'm plotting lambda 1 and lambda 0 from the map rule. I'm not using the ML expression, I'm using the map expression. The only change is q became 0.1. The prior reduced from 0.5 to 0.1. And so because of that, let us look at what happened to lambda 1, which is in blue. Lambda 1 was before how much at p equal to 0.4?
1.5.
1.5.
It was 1.5. Now it became roughly about 0.2. Why did this happen? It's because of this q. You are assuming that the previous probability that the source is taking value of 1 is very tiny. It is only 10%. And so even if you observe y equal to 1, your beliefs about x is equal to 1 is going to still remain pretty small compared to x is equal to 0. Actually, even when p is equal to 0.4, you are still going to decide that the transmitted bit was 0, even though you got 1. Why? Because this blue value is less than 1 at p equal to 0.4. On the other hand, at p equal to 0.4, look what happens to lambda 0. At 0.8, it roughly becomes 2. So if I keep on going for smaller values of p, I would say that at p equal to 0.4, this red colored line will reach maybe 10,000 or something. I don't know, some very large number. Why is that happening? Previously, it was just 1.5. Now, how did it become suddenly so large? Again, because your prior about x is equal to 0 was very large. It was 90%. And so now, on top of that, if you observe y equal to 0, it further strengthens your belief that transmitted bit was 0. And in the extreme case when q is 1%, which is actually the problem that I had given you, the situation is even more dramatic. From 1.5 at p equal to 0.4, the value reduces to maybe some really small number. So that is what I meant, that the prior acts as a dead weight. It doesn't let you update your belief too much based on the evidence. Okay. So it's almost getting close to 1 hour and 15 minutes. But I will go on for maybe another 5 to 10 minutes. Is that fine with you?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So I'll conclude by maybe 20 minutes after 10. So now we are going to kind of spice up this problem. We are going to put a spin, either leg spin or off spin, whichever spin bowling you prefer. And I'm going to reformulate the problem, ask you this problem again. Now, this problem statement is again not unfamiliar to you at all. In fact, I had mentioned to you when I gave you this the problem first time, I had mentioned to you, and this I'm repeating again. Actually, this I think happened, although I by the way, don't follow the news about Hindi movies too much, but you know, this Bachchan family, right? They got this coronavirus, and I think in those days, Mrs. Jaya Bachchan actually did two tests. Okay, she did first test maybe at home, and then she went to another test facility and she did another test, and maybe that time eventually the conclusion was that she is not infected. This is very understandable. It's common sense that you do a test, it comes out positive, and then you want to get further confirmation. So you take another test. This is very common sense. It's very understandable to all of us. And that is how you want to think about this lambda 1, lambda 0, etc. What is very common sense, why somebody would go for second test? Well, the reason is that they want to climb up or down this red colored curve, or the blue or the red colored curves. They want to get a strong belief. So my question to you is that somebody does two tests, and let us say that the test result comes out positive in both of them. Then what is the probability that she has the disease? And this I would like you to solve for two cases. One is same as before. Oh, by the way, for both the problems, you take P equal to 5%. There is no change in P. P was 5% even in that earlier problem. Even now, you take P is 5%. But, oh no, not two. Actually, I would like you to do it for three cases of Q. Q equal to 50%, Q equal to 10%, and Q equal to 1%. The one that you had solved in the first lecture was only for Q equal to 1%. Now I would like you to see the impact of the prior beliefs, Q. What happens if Q goes high from 1%, it becomes 10%? Or what if it becomes 50%? Okay. So first solve it exactly for the same case as earlier, 5% and 1%. And then once you solve that, then you just plug in different values of Q and see what answers you are getting. So the main problem is very similar as before. The only thing is that now the person takes test 2 consecutive times and the test result comes out positive in both of them. So what I ask you is you formulate the same lambda 1 and lambda 0, the posterior ratios for this case. Okay. I have already done that. And I'm going to plot just the result. I will not tell you how this, what formula I use to get this result. But I would like to see what is going on. what was lambda 1, lambda 0 values when p equal to 0.5 for the single test? Sorry, p equal to 0.4.
1.5.
1.5.
For the two test case, remember, see here, if I continue this red curve little forward, it probably will touch 2.5. So when p is equal to 0.4, the value jumped from 1.5 to 2.5. What does it mean? When you did the test again, that result came out positive, so you are more afraid now. Previously, you were afraid by 1.5, now you're afraid by 2.5. You think that now there is definitely a good chance that I have the disease. But still you are not worried that much actually. Why? Because P is so large, P is 0.4. So you're not that worried. Let us look at the case when Q is 10%. So let us again pick up some values. In the single test case, when Q was 10%, and let us say P was 40%, this lambda 1 ratio was about 0.2. At same value of P, lambda 1 became slightly more than 0.2. It became maybe close to 0.25. And look also what happens to the red curve. The red curve was just shooting up straight. Remember, red curve is telling you the belief about you not having the disease. Now that also gets modified. You are not sure anymore that you don't have the disease. This is the result for Q equal to 0.01. And again, the posterior ratios kind of change quite a lot compared to this case. This is the single test. This is the multiple test. Okay, so this is where we are going to stop. Why am I bringing this problem? Why am I asking you to look at this problem? This is because this will lead us to a very, very important and very current, I would say, some technique, some method, some algorithmic scheme of today's communication systems, 5G and 6G communication systems, which are kind of direct. The problem will remain exactly the same. Let me put it that way. If you solve this problem of somebody doing test 2 times, then exact same concept, exact same mathematics will apply to this communication system technique that we will be studying. That is one reason I'm asking you to solve the problem. The other reason I'm asking you to solve the problem is because, as I said, it puts a spin on this earlier problem of disease detection. You may have solved that earlier problem on your own, or you may have struggled with it. If you have solved it, and if you can solve this second problem also completely on your own, then that will give you a great confidence that you are totally on top of this mathematics. If you had a tough time solving that other earlier problem, well, then now you can actually look at all this mathematical and conceptual description that I have given you and see if using that you can solve this consecutive test problem that I just gave to you. Okay, so this is where we will end today's lecture.